Hi, my name is Jorge Moreno, and this is my final capstone for Management 490, for Finance. What you're looking at is an integrated finance application I built and deployed on Streamlit, a single web app that combines three things into one decision tool for any analyst. So, number one is a discounted cash flow valuation engine, which is my project one. The number two is a mean variance portfolio optimizer, which is my project two. And number three, the original component I built specifically for this capstone is something I called PAR, which means the Position Action Recommender. PAR takes the output of any of the DCF and the output of the optimizer, and it tells the analyst for every ticker what they should do, either trim, hold, or add to that position. Before I go any further, though, I wanted to be upfront about the AI usage. I use Claude Anthropic's model to help me scaffold the modular architecture, port my two earlier projects into a unified code base, and draft documentation. I authored the requirements, made every design decision, reviewed every diff, and validated the outputs against my two source projects. A full AI usage disclosure is in my README and in the driver documentation I will be submitting along with this video. So on the Home tab, you can see exactly what the app does. The user enters between 1 and 15 tickers. Over here in the sidebar, the app fetches the financial statements and price history from Yahoo Finance. So that means it's all free, no API keys. And then four tabs run in a sequence. The data flow is right here. Um, Tickers feed into the shared cache data layer. From there, three pure engines run in parallel, the DCF, the portfolio, and optionality state sentiment. These outputs converge in par, which produces the per ticket verdict and the sensitivity tab that reruns the entire pipeline under a scenario so you can demonstrate cross-component effects live. That cross-component sensitivity is one of the rubric requirements, so I'll show it explicitly later. The tickers, as you can see, need to be comma separated. So now let me load some data and see the default. So let's wait here. The data is loaded, as you can see by the green button right here. What I loaded was Apple, Microsoft, Google, Amazon, and JP Morgan, which I'll keep those as a demo because they have the clean financials. But as you can see, I can type here whichever other ticker I would like. Um, this field is also fully editable. I could put up to 15 tickers, but as I mentioned, I'll just stay with those five. Um, so here also, as you can see, it agrees that it already fetched the data. Um, Below the price history slider is the years of history. So that's how many years of daily closes the optimizer uses. The default is 3 years, which is reasonable balance, long enough for the covariance matrix to be stable, but short enough so that the regime is still relevant. I'll keep it at 3 for this demo as well. Um, but you can move it to 5 or 10 if you want it. From 1 to 10 is what we can do. Um, so perfect. Now I'll switch on to the DCF tab. So first is this one, the DCF. This is my project number one, ported into the capstone. So for every ticker, it projects unlevered free cash flow over a horizon I control. The discounts at WACC applies a terminal value and converts enterprise value into per share intrinsic value. Here is the assumption. So all of these are sliders. You can move them, edit them however you would like. Um, every assumption, as I said, is visible on the slider. Forecast horizon, revenue growth, EBITDA margin, tax rate, DNA, CapEx, working capital, WACC, and terminal growth. The defaults are deliberately conservatives, a 5-year horizon, 5% revenue growth, 25% EBITDA margin, 21% tax rate, 10% WACC, and 2.5% terminal growth. Um, Now, if we go to the per ticker valuation summary, for each stock, the app shows the current market price, the calculated intrinsic value, the upside as a percentage, and a simplified traffic light verdict. Green if it's more than 15% undervalued, yellow if it's within plus or minus 15%, and red if it's overvalued at more than 15%. Now, if we go to the drill down, we can select specific tickers. I'll stick to Apple for now. Um, so we can see behind the numbers. So the top line metrics for Apple, the market price, intrinsic value, upside, and enterprise value. Below that is the unlevered free cash flow forecast, revenue projecting forward, EBITDA, taxes, D&A, CapEx, working capital, and the resulting unlevered financial cash flow per year. Those get discounted to today and then some. Um, if we move even more down to the sensitivity, this is our WACC by terminal growth heat map. The vertical axis is WACC, ranging from 6 to 14%. The horizontal axis is the terminal growth from 1 to 4%. Each cell shows the resulting per share intrinsic value. You can see how rapid the valuation changes when those two assumptions move, which is why I exposed every assumption as a slider rather than burying them in code. Um, so I'm gonna show you. I'll move the WACC from 10 to let's say 12, and you can see it moved. Um, but I'll put it back to the 10% just um for this demonstration. Then you can see everything went back. Um, So next, going to the portfolio tab, this is my project 2, which is a mean variance optimizer. It takes the daily adjusted close panel I just downloaded, analyzes returns and the covariance matrix by 252, and runs the SLSQP solver under one of three objectives, subjected to weighted bounds. Um, The three objectives are the maximum stripe ratio, minimum variance, and target return, which you can see right here. The default is max stripe because a sharp is the most defensible single number for risk-adjusted return, excess return over the risk-free rate divided by the volatility. Then we have the three KPI metrics, which are the expected annual return, the expected annual volatility, and the Sharpe ratio for the optimal portfolio. Um, Here are the optimal weights with max Sharpe and a 40% maximum weight cap. The optimizer concentrates in the names with the best historical risk adjusted return for these five stocks. But if we can move this, for example, if I move this to, let's say, 20, you can see how it changes, which basically it dropped, which that is the trade-off. The tighter the constraints, the more diversification, but the lower risk adjusted return. That actually matters in real life because every fund has mandate constraints and they all impose the same trade-off. So before moving on, I'll put it back at 40. Um, Now going even further below that is the efficient frontier. Um, three 3,000 random portfolios plotted by risk on the x-axis and return on the y-axis, which are color-coded by Sharpe. The frontier is the upper left edge of the cloud. These are all optimal portfolios. Those, sorry, are all optimal portfolios. The red start is the max sharp portfolio. The green diamond is the minimum variance portfolio. And there's a marker for the portfolio I'm actually using right now, which I think you can't see it here. It's right there. This is the portfolio we're using. Um, and if we go even further down, there is the correlation heat map. Um, and a comparison table of the three strategies side by side, but I'll skip the deep dive on those as they were documented in my project 2 video. Now, let's go into the heart of the capstone. This is PAR, the position action recommender. This is the original component I built. Without PAR, the DCF and optimizer are two separate apps that don't talk to each other. So PAR is the only place where the outputs actually meet and produce a single actionable verdict per ticker. So at the top, the verdict counts for the universe, how many positions are flagged, add, hold, or trim, which you can see here. Um, Now, if we move even down, here's the action table for every ticker. PAR computes these signals. First, the evaluation signal. This, I'll move here so you can see everything. So first, the evaluation signal, that's the gap between the DCBF intrinsic value and the current market price, normalized so a 50% mispricing maps to a full positive or negative one. Second, the allocation signal, the difference between the optimizer optimal weight for that ticker and the 1 over n equal weight baseline. With 5 tickers, equal weights is 20% each. If the optimizer wants this ticket overweight versus equal weight, the signal is positive. I document equal weight as the baseline because the user hasn't told the app what they currently own. So that's a defensible, transparent assumption. Those two signals are weighted by user controlled sliders summed into the composite score and mapped through a threshold into trim, hold, or add verdict. Trim if the score is below negative threshold, add if the above position threshold, um, if it's above positive threshold, sorry, and hold if it's between. Now let's move up. Every one of those weights and thresholds is exposed as a slider right here. Valuation weight defaults to zero point 0.6, allocation weight to 0.4, action threshold to 0.25, and there's saturation scale sliders that control how aggressively each signal hits its bounds. Now you can see for example, the action threshold. I can move it as well. So watch what happens when I widen the threshold from a 0.25 to a 0.4. The hold position gets wider. The few tickers on a cross into the no, none of them are crossing. Let me see if I move in further. Well, none of these are passing the to the ad, but they could pass to the ad if it was enough. Um, but they stay there. I'm gonna move back to the 0.25. Perfect. Um, Below the action table is the action um is the contribution chart for every ticker. You can see exactly how much signal pushed the score up or down. Blue is valuation, red is allocation, and green is sentiment. That makes the verdicts defensible to a portfolio manager. Every add or trim has a transparent composition, and the entire table downloads as a CSV with one click, so an analyst can paste it straight into the portfolio review meeting. Um, Now I'm gonna include the sentiment, and this is the optional third signal, which is new sentiment. By default, it's off because sentiment is a tilt, not a foundation. But now that it's on, um, you can see that it auto bumps to a zero point 0.2. Now, notice that, as I said, it bumped to a zero point 0.2. The demo is immediately visible. I can deliberately cap how much sentiment can drive the score because it's a soft signal, as you can see here. Um, Under the hood, the app pulls headlines for each ticker from Yahoo Finance, score them offline with Vader. That's deterministic, lexicon-based sentiment modeled from Hoto and Gilbert's 2014 paper. The averages that compound scores over the lookback window, so no API keys, no LM calls, and it's fully reproducible. And here, let me, here are the top headlines. So these are the top headlines per ticker with the individual Vader scores, so the analyst can audit exactly what drove each ticker to each sentiment number, as you can see right here. Now notice the green sentiment bars now appear right here in the contribution chart. Each ticker score now has three sources, weighted by my sliders. I want to be honest about a known limitation, which is that Vader was trained on social media, so finance specific jargon like guided lower can score weakly. I mitigate that with the optional sentiment veto, which downgrades any ad to hold if news strongly negative. That checkbox is in the same settings panel. Now I'll go on to sensitivity. So this is a final tab, which is the sensitivity tab. This is the explicit answer to the rubric requirement that I demonstrated. Cross-component sensitivity live. It runs the entire pipeline twice, DCF, then portfolio, then par. Once with my baseline settings, once with a scenario permutation, and shows me exactly which verdicts flip. Um, so there are seven. There here. There here. So there are seven presets: custom manual mode for full control, raise WAC plus 200 base points, lower WAC minus 200 base points, cap maximum weight at 15%, sentiment at a 30% weight, a slow growth scenario minus 3 percentage points, and a sentiment veto on scenario. So let me run the WAC plus 200 points basis point scenario. That's a stress test for what happens if a cost of capital rises sharply, like a Fed tightening cycle. Um, Now, here are the inputs that changed. So first, the app shows me exactly which inputs change between baseline and scenario. In this case, the WAC would have moved up by 200 base points. Next, the portfolio level deltas, return volatility, and sharp under the scenario, with a color delta showing how much it shifted versus baseline. And here's the verdictive baseline verdict on one side, scenario verdict on the other, and any ticker whose verdict change gets flagged add to hold or hold to trim um, tag right in the table. Um, Consequently, under the higher WACC scenario, the DCF intrinsic values are lower across the board. The valuation gap shrink. The par composite score drops below the add threshold for the same tickers, and they flip and add down to hold. That is the cross-component sensitivity the rubric requires. One upstream input WACC propagating through DCF into par out as a flipped verdict, and the chart at the bottom shows the verdict distribution side by side. You can see the add count drop and hold count rise. That's a one screen instructor grade demonstration that the components are wired together highly. Um, Here. Now, to close, the honest limitations I documented in the README and driver. One, the allocation gap uses an equal weight baseline because the user doesn't upload current holdings. That's a one line extension. Two, Vader is imperfect on financial jargon, which is mitigated by the veto and the bounded weight. Three, Yahoo Finance coverage is uneven for foreign and OTC tickers. The app surfaces failures as data, never as crashes. So to summarize, the app integrates DCF valuation, mean variance portfolio optimization, and my own par component into one decision tool. Every assumption is a visible slider. The components are wired end to end. Cross-component sensitivity is demonstrated in seconds, and the full driver documentation and AI usage disclosure are in the GitHub repo. Thank you a lot for watching.